how's the simulation going? Any questions about that? Everybody got waveforms out. How long did it take? A couple hours, 3 hours, 10 hours? A few hours. Okay, that's reasonable. Any questions on the simulation? Yes?
So maybe this is already asked, but so when the simulation is going on MATLAB and then ModelSim at the same time with the same initial conditions,
Yes.
I understand that at some point we expect the two to maybe come out of sync, right? How long should that take?
Okay, so what you're asking is, given that the system is chaotic,
Yeah.
and therefore very sensitive to initial conditions, how long should it take to get out of sync? And my guess is it's only going to be a few hundred steps.
Okay.
Only a few hundred time steps. Even if you match the constants as well as you can, so using 2.75 rather than 2.66, since 2.66 is a continuing fraction in binary, and the truncation is done differently in MATLAB and in fixed point, you'll get a better result if you go to 2.75 rather than 2.66. And if you change dt, instead of being 0.01, which is doesn't match well with binary, if you go to 1/128, both in the simulation and MATLAB, that's about as close as you can get, and it will still diverge after a few hundred cycles. That's why, to verify this, I'm asking you to also do the 3D plot in MATLAB, because the double scroll structure is relatively robust.
So we just checked if we had a double scroll structure and we did. Are we supposed to like try and line up and see that what we put in the ModelSim and MATLAB is
What you're asking is, do you need it to carry it past the graphic stage of seeing a double scroll? And the answer is no. So you need to sort of graphically verify enough that you believe it when you grab this in MATLAB and rotate it, that it looks about like the 3D projection of the ModelSim version. But no, you don't have to do a quantitative match on that. This is just to show that your simulation is reasonable. Anything else?
Will the sparsity or the density of that double scroll affect the result?
Will the sparsity or density? So, there's two ways of making the simulation more sparse or more dense. One way is to change the time step. And if you make the time step too coarse, like 1/2, yes, the solution will be affected and it will be incorrect. On the other hand, another way of doing it is to keep the solution density high, but only plot every 10th point. And in that case, it will be correct. It will just be sparse. So what did you mean by sparse?
Just
This or this?
that one part.
Fine. Anything else? So the next topic that we need to talk about for Lab 1 is the on-chip validation of the solver using signal tap or another logic analyzer. But to do that, I really need to talk more about Qsys first. And to do that, I need to step back and talk a little bit about the relationship of all the tools we're going to be using in the class. Then we'll go into some details. And so we're going to be generating, in the center of all this is Qsys Prime, which takes in Verilog, and through a very long, interesting procedure, produces a gate list to put onto the FPGA. Now, parts of this process are quite fast, others are quite slow. So this is a bulky compile. For a small project like you're doing in this round, it probably takes, I don't know, between 2 and 6 minutes, depending on your CPU. That's a long time to sit around while you're debugging. So, of course, you're going to use model sim first on the Verilog. But there are other aspects of this that we need to talk about. So your Verilog is going to be one input here that you're going to link in. You might use signal tap, which is a intellectual property from Intel Altera that it instantiates a logic analyzer on the FPGA along with your Verilog. So this allows you to look at waveforms not in simulation, but running on the FPGA at full bus rate. A moment's thought will tell you that must suck up a fair amount of memory on the FPGA because there's no way to get those waveforms off the FPGA fast enough, therefore it must be storing waveforms on the FPGA, and you would be right. It uses on-chip memory. There's another source here. There's going to be a Verilog module that comes in from Qsys, which is going to represent the bus layout that you designed. And so you're going to use a graphic tool, which I think I showed you last time, in which you have a whole bunch of modules and a whole bunch of bus masters, and you think up bus slaves, bus masters. This generates a gigantic Verilog file that's going to be fed into Chorus Prime. You don't have to look at it. But you do need to use the Qsys interface module because some of the signals that Qsys generates are going to have to make it to the outside world. And therefore, they're going to have to come through your top-level Verilog to get to the outside world. So there's going to be an interface module that you instantiate in your Verilog. We'll talk about that. There also are some non-Verilog items that you can include here. For instance, memory image files, which are a fairly simple binary representation of how you want to set up the internal memory blocks that you've instantiated, if any, on the FPGA. So if you had a ROM, for instance, that you wanted that generated a sine function from a phase angle, you could slurp that in as a memory image file. This is all software. Then the output of this is going to get blasted off to the FPGA, which for logical purposes I'm going to separate into the FPGA side and the hard processor side, the ARMs. The ARM has DRAM associated with it, about 1 gigabyte. That's managed by Linux. You don't mess with that too much. The FPGA has DRAM associated with it, which you can use any way you like. There's about 64 megabytes. And what the code I'm going to show you today uses that 64 megabytes as a driver for a VGA display. In other words, it uses it as the frame buffer for the VGA display. And of course, you're going to have another input, so you're going to be generating this, you're going to be generating this, and of course, you're going to be generating C code that runs on the HPS. So every project you do is going to have three source files, so to speak. There's going to be a C code source that runs on the HPS, except in the most trivial cases. There's going to be Verilog source, which glues together all of the hardware on the FPGA. And there's going to be a Qsys source, which is really a graphic layout, that tells Verilog how to hook all these pieces together. Any questions? Yes.
Well, where does Linux fit in all of this?
Linux runs on the HPS. So there's I haven't drawn it, but there's an SD card here. And there's a boot process. Linux boots up off an internal ROM. It bootloads the Linux image off of the SD card and starts to execute. It boots in maybe 10 seconds. That's a full Linux distribution. Has all the usual stuff. You want to edit in Emacs? Have at it. So, one further detail is that the FPGA, which I divided into into FPGA side and HPS side, then has a memory map across this boundary. A memory map which associates structures on the in HPS memory to locations on the FPGA side. There are two buses. There's the normal AXI bus, which on the HPS side has a hard fixed address of C000_0000. Now, in Verilog, you can put in the underscore because Verilog ignores underscores in the middle of numbers. In C, you can't do that. And I'll probably slash zeros. So and then there's the AXI lightweight bus, which is narrower and slower, which has a base address of FF200000. So from the HPS side, every bus address that you mess with on the FPGA is going to be in a range starting at hex C000 or hex FF20. The size, the span of this boundary region is about a gigabyte. One thing you're going to do in Qsys is then you are going to strip the C off, or the FF2 off, and assign, so to speak, local addresses on the AXI bus. So if we look at the H to F, HPS to FPGA, H to F AXI master, we come down to the SDRAM, it is slave 1, and the address goes from 0000 to 3FF, FFFF. There's no C on there. That's because the C gets stripped off on the FPGA side. It's implied by the fact that you're on the AXI master. And So this is an address which is local and the range onto the FPGA, and it must be unique. There can be no overlap in that range.
How much of this layout is stuff that was just set up for the system in general, or is stuff that you set up yourself?
C00 is hardware, real hardware. You don't mess with that. You cannot mess with this. These addresses you can change any way you feel like, as long as the span is hexadecimal 400000, because that's the physical size of the actual SDRAM, which is 64 megabytes. So if you wanted to put a 1 in front of here, or add a hex 1000 to both of those, it would work. But why bother? But yes, these are, you choose these. And by the way, there's some on-chip static RAM, which is also on the H to F Qsys master. The slave 2 is on the Qsys master, and it has an address of hex 800 0000 through 801 FFFF. So these two cannot overlap, because they are on the same master. A master, every address on a given master has to be unique. On the other hand, we go down to the AV config module. This is on a separate master. This is on the lightweight master, and that has address 3000 because it's a different master that does not overlap SDRAM memory because it's on a different master. It's a different bus.
Can you repeat that last sentence one more time? What doesn't overlap? What?
Every address specified over here on a given master must be unique and cannot overlap. Addresses on different masters have no relationship to each other, and therefore the AV config address, which is in the range of numerical range of the SDRAM, does not overlap with it because it's on a separate master bus. It's maddening. It's so complicated. Yes?
Okay, so when I first open up the Qsys draftable interface, what is it going to look like? How much of this stuff is already going to be populated?
If you start with a new project and open Qsys, all you will see is a clock, nothing else. Nobody in their right mind does that, right? This system is so complicated that you're going to start with a project which works and modify it.
So we're going to download the files to your VGA project, and it already is all set up.
Absolutely. Otherwise, you won't finish before the end of the first lab setting up Qsys. It is really complicated. And the top level is only the beginning. It turns out that the VGA subsystem has another set of modules internal to it that is as big as this and have the most obscure settings you have ever seen. I read the manual. I read the manual 10 times. If I hadn't had an example, I never would have gotten this set up. Don't start from scratch, folks. There's too many variables. Let's pop back up to the page. I'm talking here about the SDRAM 640 by 480 16-bit color, which is the project in Lab 1, specified in Lab 1, to to use as a starting point for Lab 1. And you are going to want to hop to the bottom line here, you're going to want to download this zip file, unzip it, and see if you can make it run before you start messing with it. So the Qsys layout we just talked about for this, and to give a slightly broader background, there's the phase lock loop, the clock, the ARM system, which has a whole bunch of IOs. By the way, there's an F to H axis slave. F to H axis slave. That's the FPGA can act as the bus master and write to ARM memory. You talk about shooting your foot off. Don't do that without thinking very carefully about Linux management. But there's a big ARM 9 specified. My system has SDRAM for doing the video, and how can you tell that? Because there are 3 modules that are required for video display. One is AV config, auto video config, which sets up the music, the sound interface and the video interface. DMA translator, pixel DMA controller, and the master for that the master for the DMA controller goes out to the VGA subsystem, and then the DMA master goes back up to SDRAM. So the display subsystem is going to be using the same SDRAM slave port as the HPS can write to display to the VGA. How do you get from this Qsys abstraction to the outside world, to the monitor you're going to plug in? Well, the answer is, not only is there this bus structure, which is internal to the module that's going to be generated, and you're never going to see that bus structure in your Verilog. There are going to be signals that you can export, in this case called VGA, VGA lock, clock, and reset. And anything in this column appears in the interface module and therefore can be referenced in your Verilog. So the signals that you export, and you get to click on anything over here, double click to export. You get to click on any of these and export them to your Verilog file, where you can mess with them or use them. So there's 2 interfaces here. There's going to be the Qsys interface that allows modules to talk to one another, and all of the Verilog wiring which is done to wire these together is invisible to you outside of the module which is generated by Qsys. And there are then the signals which are exported, which will be visible to you in your Verilog. Oh, I forgot an arrow. You need these addresses all the way down in your C code. So the addresses that you generate in Qsys that you type in and deal with any way you want, you're going to need when you actually write C code, because you're going to be doing absolute bus addresses in the C code. So Qsys sets up big internal structure. Then the top level Verilog This is going to be the module that you have access to and can write into, put modules into. It's going to have a very long list of I/O pins because the FPGA is connected to all kinds of stuff on this board. Whole bunch of I/O signals. I wired up some of the hex displays because I was using them for debugging. And then the module which is exported from Qsys is instantiated in the top level module. You find that module in a subdirectory. There's going to be some directory where you have unzipped the file and you do the Qsys compile, and there'll be a subdirectory, a subfolder off of that called something like synthesis or the system or computer system, and in there will be a .v file, which is this interface file. It's not the whole disaster. It's not the million lines of Verilog that's generated to generate the Qsys. It is only the interface, the exported signals. The exported signals. So the exported signals for instance, for the VGA subsystem are here. These are the names that you associated with the signals in Qsys, and these are the connections to the outside world. In this case, we're merely taking the output from the VGA control system and hooking it directly to the H-sync, V-sync, and RGB controls of the monitor that you're going to attach to the FPGA. There's another stanza here which connects the SDRAM control lines, of which there are a bunch, and then a whole separate set for the HPS side of things, which you really don't want to mess with. This is a fairly big file. This version has been formatted into sections for your viewing pleasure. The default version that comes out of Qsys has no subsections. It's just one long blast of I/O linkage. So again, what I usually do, and what most people do, would be to change as little of this code as you possibly can when you add a new module. Add some signals, subtract some signals, but don't start from scratch. Just too many things to type. So then to say this again, the Qsys HPS master is connected to SDRAM so that the HPS can read right to the VGA screen. Each there's going to be 307,200 locations in SDRAM that represent one image. You can write to those locations, you'll get pixels, and the base address is C000, and the address is used in the HPSC program by some sort of stanza like this. Pound define SD base is C00, define end as this. Span is, of course, just one more than this. And we need the span and the beginning and the end to appropriately map the physical memory into Linux virtual memory. We'll talk about that. So that's the heavyweight bus. And then there's the lightweight bus starts again at FF2 and goes in this case for something like X5000. But what's this? C9? I didn't mention C9. Those are local peripherals on the HPS side. Those are LEDs you can blink on the HPS side if you like blinking LEDs on microcontrollers, and who doesn't? But generally speaking, oh no, I'm oversimplifying. I already chopped that stuff out. I suppressed it. This is character based. This is the address. So C9. Uh-oh. Let's go back and look at the damn Qsys now. What is C9? C9, top level Qsys. C9. Is there something that's at C9? 900. Character buffer down there, yes. And that is on the.
So that's writing text to the VGA, I think.
That's writing text to the VGA. It's a separate chunk of memory. The character buffer is on the heavyweight bus because you want it to be fast. That's why it starts with a C. So, we're going to, for virtually every project, we're going to be specifying Qsys modules and addresses. Now, for this project, it's already laid out for you. You don't actually have to modify any of the VGA stuff for this project, for the Lab 1. You are going to have to add Verilog because your solver is going to go here. Oh yes, you do. Okay, for testing you don't necessarily. Yes, you are going to have to modify Qsys because you're going to have to add parallel ports. You're going to have to, at the end of this Qsys layout, you're going to have to add parallel ports so that you can communicate from the HPS to the Verilog that you're going to be using here. So one side of the parallel port is going to be on the Qsys bus, and the other is going to be exported to the FPGA so you can use the signals. So, what's the level of confusion? Low, medium, or high? There's lots of stuff going on here. And there's no simple way to separate it because it all happens in every project.
Okay, so you open up the Qsys layout again?
Sure.
Okay, so there's this big section on the far left side where it shows signals being connected to other signals. What's actually going on there?
So to output the system clock to a module, you look at the SDRAM clock, and if you were to drag out a fresh SDRAM module, you can't do that because there's only one physical SDRAM. But if you dragged out a fresh module, there would be no dot there, and you have to click on this intersection to give the SDRAM a clock input. Now, if you hover over this dot, you can find out some information like what the master source is, what the destination slave is, and what its bus share is. And you can change the bus share to change the bus priority. But the way you make connections is to click dots. Click intersections between wires. Clearly, not all these are used. These are not used. And I found this very confusing at first because each lane here represents a different master. Each vertical wire is a different master. Each horizontal wire is a connection to one of the masters.
So what's going on where you've, it looks like you've wired your H2F hardware or heavyweight Aximaster to S1 the SDRAM, but that also is wired to a different plane.
That's perfectly fine. You can have two masters wired to a single slave, and the bus structure resolves the conflicts. So it is a multi-master, multi-slave bus. The bus itself, the code you never see, the Verilog you never see, generates contention control and resolves contention. So you can pretty much hook these things up the way you like and it'll work. Obviously, if you have two masters hooked to the same slave and you start pounding on this thing as hard as you can, you may overload. You may get to a rate at which this SDRAM can no longer read and write. It'll go at 100 megahertz, but you could saturate it. Particularly if one of these is a DMA burster. What else about this? Oh, there's two resets here. All right. I don't know why. Every example I've seen had two resets connected to each module, and so I did. It's equivalent to, sacrificing a chicken just for luck. I don't know why.
Does the system reset when reset goes low or goes high?
I have no idea. It's internal. You never see this bus.
Well, it matters for stuff like the integrator code you gave us, which seems to be assuming it resets when it goes low.
That is in the Verilog code. That is not on the Qsys bus. So the signals that come in here through the exported signals have a polarity that you control. And that you have to worry about that. But this is all completely hidden from you in terms of Verilog.
So is everything we do for the Qsys clicking buttons on this? Or do we actually write something?
Everything you do with Qsys, you do by this WYSIWYG, this point-and-shoot interface that wires stuff up. You type in fields here to change addresses. There is an auto address feature. You click it, and it will guarantee that there are no overlapping addresses. That's cool. Downside is it changes every address, and so you get to change your C code. But all the design is here. Now, what comes out of this is actually some gigantic text file, which is then slurped into Qsys and compiled into Verilog. You could, in principle, edit the text file. Don't. It's like quantum mechanics. You never really understand it, but you do get used to it.
So are the little rectangles where it just comes out into the connection?
These little guys here,
Is that like external interface?
these are just non-connected. This particular connection was exported instead of connected on the bus, and so was the HPS I/O was exported to the FPGA rather than connected on the bus.
Can you both hunt the signal on the bus and export to the FPGA?
Depends on the wire. Generally, yes. However, you have to be careful. On these on-chip SRAMs, there's two ports. They're dual ported, if you want. You can hook one to the bus and export the other one. And when you do that, now you have a high-speed scratch pad that can be written and read simultaneously from the HPS and the FPGA fabric. No synchronization necessary, two ports. That's a very powerful interface between the two. I use them all the time. The two ports, the two slave ports are completely independent. I have an example of that on the debugger that I logic analyzer. So in this case, the only thing you really need for a logic analyzer is you need a high-speed memory that can grab data off the bus as fast as possible. Actually, out of the FPGA as fast as possible. So the analyzer buffer here is on-chip memory. It has two ports. It has two slave ports. One is hooked directly to the high-speed to the Qsys master, and the other one is exported directly into the fabric, so you can connect an arbitrary signal to that to be logged into memory. So there's two ports, one on the bus, one not visible from the bus, but it is visible from the FPGA. Likewise, the control buffer, which is another block of RAM, has one port on the Qsys bus going back to the ARM, and the other port is exported into the FPGA fabric so that the HPS and the FPGA can handshake through memory. I like that particular structure a lot. I use it a lot. You can also make an extremely fast display memory by dual porting a memory block so that one side goes to the VGA subsystem and the other side goes to your GPU that you've just built. More questions? So what I think you ought to do here is to, oh, and this program, this HPS program does all kinds of stupid graphics. It puts up some blocks, it draws a bunch of disks, it draws circles as fast as I could draw circles, to the point where thought I was going to throw up by watching them come towards me. It draws lines. It tests graphics primitives. Really, is what it does as fast as possible. And running this thing wide open with no delays, I couldn't crash VGA. So the system is throttled appropriately. But if you look at the HPS program, it's going to start out by doing the usual stuff of importing a bunch of libraries. And oh, you're going to compile this on the target HPS, by the way. The C compiler runs on the target HPS, yes.
So then, how do we get the source code on target HPS in the first place?
Well, in Lab 1, it gives two suggestions. There's actually three ways to do it. One is, if you're completely insane, you edit directly on the SD card. Don't do that. First of all, SD cards lose data. Secondly, Vim is a terrifyingly awful editor, in my humble opinion. So the best way the way I find that I get the best data reliability is to edit in Notepad on the PC, and then use MOBA extern to SSH into the HPS. You can also download an SSH client directly to HPS and SSH to it. So there's the bus addresses that I copied out of Qsys. All of the addresses necessary. a list of graphics primitives, which I'm not going to talk about right now, but it's text, boxes, rectangles, lines. It's what you need for these basic courses. I wrote a rectangle rendering GPU just to see if I could do it, but this is not part of this. A pixel macro because I want it to go fast. Then the heart of this is that you have to do some pointer diddling to find out where the real map is. So the first thing we're going to do is open a device called /dev/memory. You know, in Linux, devices are in /dev. You all know that from someplace, or you better look it up real soon. /dev/mem is a kind of pseudo device that gives you a way of directly dealing with memory structures. And what we're going to do is to use that device to produce a virtual address which is linked to a hardware register space is linked to a physical address. So physical address, address span, the size, which by the way has to be in pages of virtual memory. Has to be in page count. There is a Linux function mmap which then takes that base and that span and gives you a virtual base with the same span. If you write outside of that virtual base, it's segfaults. So this gives you a way then, gives you a window into physical space, which is protected because segfault's outside of that, and it assumes that you know what you're doing because you're running as root. You could do anything you want. The pixel address, pixel base, is going to be an SDRAM base with the span of SDRAM. In other words, we're going to have a very large virtual pixel map. In fact, enough for about 300 frames. We're only going to use the bottom few percent, 1 or 2% of this for the frame buffer. But then once we've got this virtual base, we can manipulate the pointer to the correct form. And then, so we get a VGA pixel pointer, then we can go back up and look at this VGA pixel macro, and we find that we're going to take the virtual base, we're going to multiply y by 640 and add it to x shifted by 1. Shifted by 1. Okay. And that's because of the size of the word. And the result is a pointer to a pixel on the screen in coordinates of 640 by 480. So now you can feed this macro x, y, and a color, and it will put a point on the screen at the correct location. By converting to a virtual pointer, which is then n-mapped to the physical pointer, which causes a memory write to the FPGA across the AXI bus, produces a memory write to the FPGA across the AXI bus, puts the value in SDRAM, and then when the VGA controller comes back around to that pixel, it grabs that value out of SDRAM and puts it on the screen.
Why SDRAM and a do while loop, which never runs more than once.
This is obsessive programming to make sure that no matter what context you put this in, it is not confused by other code which might accidentally be in the same block. So this is just a wrapper. The do while zero is a wrapper to make sure that the code stays together and is not affected by other code. It's often used when you put code into a macro. Come with lots of questions next time. There's lots of stuff going on here. And there's no easy way to start except to start playing with it. Download the zip file, compile it, watch it run, make one tiny change, and see what happens. The usual way you learn to program, in other words, except everything's changing at once in this case, because there's a memory map that you can mess with, there's the C code you can mess with, and of course you're going to have to build a solver in Verilog. Now what I'm going now the debugger that I mentioned, this is just a teaser for next time. The debugger that I mentioned packages this all up so that if you merely drop your solver into a certain spot in a Verilog file, its results will be recorded for you, and you can read them out on the console, on the HPS console, and the VGA. We'll talk about that next time. I'll be in lab this afternoon, off and on, or most of the time, depending on how many people are there. Of course, I'll be in lab tomorrow and the next day. Do not wait till your lab period to build the solver. I will get you lab access. I will ask for that lab access for everybody today. Thank you.